Hello, everyone, and I'm very glad to be here, and I thank the organizers for having me here. So we are all here because, as you know, all of you, machine learning does wonderful things. And actually, the point is that it's not exactly that it does wonderful thing. It can do wonderful thing. Because in order to make it work, you have to have a number of details to make it right. When you are trying to train a deep network, then there are plenty of things which can make it work, or quite the contrary, which compromise your success. So why is this a problem? Just because, you know, in quite a few domains, and machine learning is one of them, you don't have a killer algorithm, right? Something which works all the time and very well. And you have the choice of the algorithms and the choice of the hyperparameters, which are essential in order to get something. And so the question is, in order to do the knowledge transfer to industry and to the society at large, this is a problem because usually in order to make something work, you have to have a good student and to say, typically make it work and you will have your PhD or something, right? So the question is now, what we have now is that the machine learning field has a new problem, which is a kind of meta-learning problem, which is now, how can you find, for a particular problem instance, let's say, how can you find what is the right algorithm and what is the proper hyperparameter setting, right? So this is a key bottleneck, all the more so as we have this shortage of data scientists, which is advertised everywhere. And the good news is that more machine learning can solve the problem of machine learning. So I will try to tell you a little bit about the state of the art and try to say how you can formalize this as a game. And then I will, if time permits, I will tell you a little bit, share with you a little bit about, say, women in data science, right? So this is an old problem, a very old problem. Actually, the fact that there is no killer algorithm was known at the beginning of, say, the 70s. And then it defined a problem, and the Rice was a pioneer. And you see, typically, it looks so simple. If you can, say, define the problem space, and then if you could describe a problem, given, say, a vector of features, if you could have, say, the criteria, let's say that this is the performance you want to optimize, then you could predict what will a given algorithm get as performance on your problem, and then problem solved, because typically all you want to have is to select the algorithm which hopefully will get the best performance, right? So now it's much harder than you think for a number of reasons, and one is because we don't know how to describe a machine learning problem, right? So before that, people are trying to say to learn a performance model, right? Or they are turning to hyperparameter optimization. I won't have the time to speak about programming by optimization. And typically, because the problem is so hard, you know, you launch challenges and you ask the international community, what can you do on this? And there were a number of challenges, international challenges, organized on this topic, right? And then a little bit of shameless advertisement. There will be very soon a challenge about how to automatize deep learning, organized in collaboration between our lab and Google Zürich. Okay. So here you are trying to learn, to predict what will a given algorithm get on a given data set. Right? So now you have to just, as usual, when you have a machine learning application, you have to have examples. Here, an example is actually a data set. And you have to describe them, and then you have to learn the model. OK, very simple. But what is difficult is to have a representative benchmark, right? And then you have to run all algorithms in your portfolio on all problem instances, so it takes a lot of time. And then what is perhaps the most critical question is how to have a good, cheap representation of your training set, right? Because you have the fact that a data set is a distribution. And in order to describe a distribution, then the question is, it should not be more expensive than just running, try and see what works. Okay. So basically, this is the question, right? So what do people do, and what was explored in the previous challenges? Well, we were just forgetting about trying to learn a general model. We're just considering one data set. So now you try, and you see what your trial, that is one algorithm, and the hyperparameters, what it gets, right? And then you are just in front of a black box optimization problem. Okay, trying to find the optimum of this function, this surface response, and you're trying to see what would be the algorithm and the hyperparameters which would do the best. You try. This is a black box. And not only a black box, but also something which is very expensive, because when you do a trial, then this means that you have to run all the learning algorithm for some time, right? So this is where you are, and basically what works here is at the same time you are trying to build a surrogate model, that is the function that you don't have. You are trying to estimate this, so this is, again, machine learning. And then you have something which is very nice, because you had, so the black points here, this is something that you're sure of, right? And then this model gives you what you know, and also this is all the uncertainty about what might be. And because of this, you are trying to find where would be the most promising next trial, right? And all this is what is called now Bayesian optimization. Okay, so you see what you do is this, right? So you have this. You can see that here the most promising point is this one. You are trying to minimize the error, right? So you try, and then you get bad luck. And now what is the next trial? Now this is the other one here. And then you go on, and in the end, you get something which is the best that you can get within your computational resources, right? Within your budget, right? Okay. So, and this is exactly what is working, what is implemented in the winner of the previous AutoML challenges, which is AutoSklearn. Before that, there was AutoWeka, but it was long ago. And now this AutoSklearn, which was built by Matthias Föhrer and the team of Frank Hutter in Freiburg, is actually available, and it works, right? There are many other approaches. I don't have the time, of course, to speak about this. I will just mention this. And then I will try to tell you that here we can perhaps use another approach to tackle this same problem, as if it were a game. So I guess that all of you heard about one of the last, I would say, major things which were done in machine learning in the last years, which was AlphaGo and AlphaZero and all the others, right? So you remember that this was the AI challenge just after that the chess game was solved. Was it really AI or brute force? I don't go into the detail, but at least we all knew that playing the game of Go could not be solved by brute force, right? So basically what you had here is that you had the game tree here, okay, way too large to be able to explore this. And in particular, what you don't have is a good function telling you how good a position, that is the situation of the Goban, how good it is, right? So what do? Well, you try, and then this is the way. So this was done as, say, following Cox's and Sebag approach of upper confidence tree. This was an instance of the multi-arm bandit problem. Okay, which I will, so basically what you have is that you have this huge game tree, right? There is no hope you can explore this all. So what do? You break this problem into small problems. What you have is that you start, as usual, at the top of the tree, right? And then you are wondering yourself, what is the best move I could do? Well, and here you applied the multi-arm bandit. You are trying the optimism in front of the unknown. You are still trying to do, well, if everything was working well, what is the most promising move? And then you do this, and again, 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 until you arrive at the frontier of your known world, right? So now, so far, you've been exploring the game tree until finding and following the best path, and with the nice balance between exploration and exploitation. Now you add a node, right, and a new node, and then basically at this point you would follow a random policy until arriving the random phase, until arriving at the end of the game, right? And now at the end of the game you know who wins, right? And now as you know who wins, then you can update all the paths you followed and decorate each node with this average value and the number of times that you've been into this node. Okay, is that clear? So now the good point is that what is working right now behind AlphaGo and AlphaZero, apart from the fact that there is a huge computational power behind, is the fact that decorating each node, if you have a very big tree, this is a little bit too much. So perhaps instead of having this value attached to each node, you could have a neural net and then generalize over the whole tree space. And basically that's it. So now, how do we do this for, you remember this talk is about finding what is the best algorithm and what is the best hyperparameters, but also pre-processing of the data in order, in the end, to win the game, to have the best possible value at the end, right? Well, the good point is that you can turn many things, and especially the sequence of decisions. You can, when you have a sequence of decision problem, then you can turn this into a game. And that's a very nice thing to do. And also there is a very good point, which is the fact that all the students, they are just convinced that they are not working, they are playing, because it's a game. So they can work and work, and that's very nice. So, so the idea is that you do this, right? And then this is how we designed the mosaic algorithm, which stands for Monte-Carlo tree search for algorithm configuration, selection, and configuration, right? So what you get here is that you have something which is just, well, the S is the beginning of your machine learning pipeline, right? There is the algorithm you choose, there is the beginning of the pre-processing and the beginning of the hyperparameters. And A is your next choice. This is something you're just wondering, should I apply, say, I don't know, a batch norm at this stage or not, right? And so you have something which is, you have this. This is the value of doing action A, choice A, in state S. And you have something which is just you average on the value, that is here the performance that you had on all the trials you made so far, right? And now this gives you a policy. So this is just a softmax. You're trying to see how good is to have this, to choose this action in this state, right? And now when you are, say, making your decisions along the tree, then you would use this. You can recognize this is something which is the exploitation, which will tend to favor the best games, the best moves. And this is the exploration, because if we are only if we are only doing exploitation, then we'll miss the global optimum, of course, right? So this is how it works, the mosaic, right? And now let's see a bit what is the search space. Well, you will find here, instead of finding all the moves in the Go ban, you will find basically all the choices you have typically in Scikit-learn. You have whether you should, how you should encode the categorical variables, how you should impute the data when you have missing values, which is just a nightmare in how you should rescale, okay, what preprocessor you should apply, and so on and so forth. And for the classifier, well, so this is again the preprocessing. Okay, I guess that all of you know this, so I will be short. And then you have this, more of the same, and so on, and so forth, and so forth, and so forth. Yes. So now, as you all know, when you're doing optimization, well, something which is very important is how you initialize. You are not with a convex problem, right? So depending on where you start, you will find something which is real great or so-so. So now the question is that what is important here is the meta-learning initialization, because you have to say to initialize your model, the Q I mentioned just one slide before. And then you would do this because you have your data set, which is described by a bit of features, and you just retrieve in your archive the data sets which are like your new data set, and you would initialize this. We can discuss, I hope there will be questions about this, because really there is much better to be done here. Okay, and once you're done, you find plenty of solutions, and then of course, you know, ensembling is a great thing, because if they are sufficiently diverse, then this is the wisdom of crowds. Okay, so this is the ensembling. And then we were comparing this to the mosaic. We were comparing this on, say, 100 problems from the OpenML repository, which is maintained by Joachim von Schoren. And then the budget was small by the scale of deep learning, but still 1 hour per data set. And you see, this is what you get. So what is this? This is the rank of the algorithm. So if an algorithm was always the winner, it would get the rank 1. The lower, the better. And you can see here that the mosaic, which is the blue one, does well. Okay, compared to AutoSklearn, which I mentioned, and TPOT, which is an evolutionary optimization algorithm meant to tackle the algorithm selection and configuration. Okay, and now you can see here, this is a kind of legend studies. You can see here what are the performance, so just compared to AutoSklearn, when you're considering the vanilla, okay, no sophistication, when you're using the ensemble, when you're using the meta-learning, and you can see that here, meta-learning initialization does a lot, and when you have everything together. So just to conclude on this, I would like to save a little, some minutes to speak about the women in data science. So just to conclude this, you have the fact that it works, that definitely a lot of work is done during the initialization. And now this raises the question whether not only is it very expensive, okay, because you have to have the benchmark and you have to run to find what is the best setting for each algorithm, for each data set. But also the question is whether we can overfit this benchmark. You remember that in the old years, many of us were overfitting the Irvine repository. You might remember that in, say, less antique years, many of us were overfitting the NIST. Okay, so now the question is it possible at the meta-learning level? I guess it is. So, okay, I would say that now a very interesting research perspective is to build meta features. We have those many machine learning problems, right? And we are tackling everyone as if it were a new world. And now the question is that if we had really good meta features, then we could say kind of organize this zoo of machine learning problem in a well organized way, and we would know what we were doing much better. Okay, so this concludes my technical talk. And now I've been asked to share a little bit with you, you know, life and all those things, right? So you all know that there is a gender imbalance, right? And the bad news is that, so those are actually rather recent figures. They were collected in École Polytechnique in France, but 2 years ago. And the bad news is that after one, you know, glass ceiling, there might be others glass ceilings, right? So, because what we can see here is the fact that although those girls, I think that there is something like between 20% and 17% girls in this engineering schools, you can see that still in the domains which are, to say the less, which are the best paid, there is an underrepresented, the women are underrepresented here, right? And something, I don't have the answer, something is, there is sometimes a very strong impact of very slight differences. Typically, what people found is that you see in those two domains, right, 21st century energy and sciences for environmental challenges. The technical contents is the same, almost the same. But you would find many more women here than there. That's interesting. Why is it so? I don't know. This was general. But now data sciences is something special. Because we are dealing with data. And in all domains where the data are acquired from the real society, the real world, right? Those data, they reflect the prejudices of the whole society. And if we are building models based on those data, it means that we are putting in stone the prejudices which were true yesterday and perhaps also today. And that's a bad news. You can see here that this world is a world of men and the Barbie CEO. Okay, and there is something, I don't know whether it's the right place to see this, but still, you know, there is another point which is a bit bizarre. I mean, there might be several, not only a single prejudice. And then the question is whether we should unite the fights. So, so typically this is very important. I'm working also on using machine learning for human resources, for hiring. And by the way, we are hiring, okay? And so this is very important to know how to check the prejudices in the data, how to check the biases. Okay, and then one step further. What is the cost? We want our share. That's fair. But which share? This is, I mean, the first claim in this slide. This is usually one of the claims which is the most not well received by the audience. Saying the fact that we might have to sacrifice being nice in favor of being efficient. I don't think this is a real choice. I think that this is just because of the, well, the prejudices, right? Someone who is fair I don't know, might be weak. So again, and then the last point, which is from the book of Three Guineas from the Virginia Woolf, is the fact that I like very much this book. I'm done. So the point is that we want our share, but there are several ways to get it. One might be to say to devise the rules of another game. One might be to try to win this game, and this is different. Thank you very much. Yes.
Hello, thank you very much for a nice presentation. So I have a question about meta features you mentioned, because I know some people who would say that it's not even possible to, well, I can stand up, sorry. So that it's not even possible to achieve something like this, because even small changes in data can, you can come up with totally different results, or the same algorithm is not working, even though the data are very similar. So this is what a lot of people say. So do you think it's even possible to actually achieve the meta features you mentioned, to define them?
At the moment, I don't have the answer, right? But if you are saying that some of the features might be landmark features, that is, what you get from very simple and cheap algorithms, then this kind of features could be efficient, right? There is also a general objection against against solving the AutoML problem, which is the no-free lunch theorem. But I think that this just doesn't hold here, just because you know the no-free lunch theorems. They rely on an assumption which is all problems being equally probable, equally likely, and this just doesn't hold. If you're going to Wall Street, it's to win, not to lose. So there is something which is different in the distribution of the problems from the real world. So this is typically why we can have hope. But that's what I can say.
Thank you.
Oh, thank you for your talk. Actually, I would like to ask you a question. So Bayesian optimization is often based on Gaussian processes, right?
Right.
So where your surrogate is based on the Gaussian processes, where you define your kernel such that you basically can model the dependencies between function evaluations, right? As I understood correctly, in your Bayesian optimization, you don't use Gaussian processes, right, to model your function.
Actually, it's not mine. It's AutoSklearn, and then we discussed this quite a few times with Frank Hutter. And then apparently, they tried to use Gaussian processes, and in the end, they fall back on using random forests, just because it was more efficient. But I mean, in this case, because the problem is that they couldn't get the kernel right.
Yeah, actually, it's my question, because mostly people use kernels because they can kind of choose kernels based on the knowledge they have about the function, right?
Right.
It can be either smooth or noisy.
Right.
And it's a question about tuning neural networks, because like, what do we know about how the space actually of the function, how does it look like, how the dependency between the function and version, is it like whether we can do it with the kernel or not? What is your feeling, like whether it's actually a good idea to model, I don't know, parameters tuning with kernels or not?
So the beginning of the answer is that we would like to have the kernel right. Okay, this would be the first step of the road. And in order to have this, we would like to have a kind of distance or similarity between two, say, machine learning pipelines. Okay. At the moment, we don't have it, but you know, if we had solved this problem, then you would have it. Because you could say that two, say, machine learning pipelines are kind of similar if they behave the same on the same data sets. So basically, if we can solve the problem, we will have the kernel. But at the moment, at our point of the road, they tried it and tried again. I did it myself. But obviously, they couldn't have a good kernel in order to achieve the Gaussian process in the, the space of the machine learning pipelines is a bit wild, right? Because
yes. Yeah, thank you.